Hello and welcome to the introductory video of the course Elements of Mechanical Vibration. This course is a 12-week course and will be conducted by me, Ashish K. Darpe from the Department of Mechanical Engineering, IIT Delhi. So I shall give you a brief background of the need to learn mechanical vibration as a separate subject, and we will have an overview of the contents of this particular course. So if you really look at any mechanical system or any aerospace systems, it is hard to imagine any of them without rotating equipment. So most of our mechanical systems have rotating elements, and they are the source of dynamic forces which on a flexible structure generate vibrations. So these mechanical equipment are the source of major design issues. For example, a typical gas turbine engine, as shown in this particular figure, is one of the complex mechanical rotating equipment which, the design of which is always been a challenge, and the successful robust design is always impeded by the vibration issues. So vibration becomes one of the major irritant in the final design of such complex mechanical system. Another example is of a satellite structure like the one which you see here, particularly the imaging satellite, which has cameras to take pictures of the terrain on the ground, and a slight vibratory displacement or a disturbance to these cameras, which are situated hundreds of kilometers above the ground, can cause distortion in the pictures that are taken. So this example here shows a straight highway here which gets distorted because of the vibrations, which could be of the order of milli or micro vibrations, and such vibrations are a major challenge to a successful operation of such cameras. So vibration is again a major issue in the proper design of such an equipment. The other example is in the naval systems, where many mechanical equipment are housed inside and are mounted on the structures connected to the hull. And so if these equipment such as an water circulating pumps, which are many inside the hull, they transmit their vibrations to the ship hull structure. And if the hull vibrates, it radiates waves, sound in the fluid around it, and it's like asking for trouble because you are signaling your presence to the enemy submarine. So in naval system design, vibration is again a major irritant and a major challenge to keep stealth characteristic to the best. Vibrations are not always a problem, so sometimes vibrations are actually put to good use. For example, this music box that you see here, it generates beautiful melodious sound, and if you have opened this particular music box, internal system here will show you that there are these series of cantilevers which are vibratory systems excited by the drum, and it generates sound of an appropriate pitch and quality. So vibrations are actually put to use in this particular case, and you need to design the structures to radiate appropriate sound. Well, with this background about the vibration as a phenomena and its importance, let's look at what is in store in this particular course for you. So we shall begin with a simple vibratory system. We'll take an example of a motorbike and look at it as a simple single degree of freedom system. We'll look at how to model it, how to find natural frequencies, and we'll look at different kinds of dampings which are there in the practical vibratory systems. Now, some of these dampings are sourced to the dashpot, which you will see in the automotive suspensions, but there are many systems where, for example, in these steam turbine blades, where the Coulomb damping or a dry friction damping is actually designed into the system. And so we will look at different kinds of damping models and how to implement them in the governing equation of motion. Then we will explore as to how to find the response to arbitrary excitation. For example, if this bike goes through a ditch or over a speed breaker, how does a rider feels the response to such an arbitrary excitation? So this topic is another important one in the preliminary topics. Then we will look at the forced vibration theory, where, for example, in this, again, this vehicle will be subjected to harmonic force excitation from, maybe from coming from the engine or from the ground. So how to find the response to such excitation functions? We'll look at the importance of transmissibility in the design. And we have some setups in the lab where we can look at how the forced vibration of this platform on which you can stand for as a fitness machine, how to model such fitness machine as a vibratory system and generate the response. Okay, so this is just one of the examples that we will look into. The other topic, once we are done with the basics of simple vibratory systems, is to look at the same system by increasing the degrees of freedom. For example, this vehicle can be modeled as bouncing and pitching both, and so this vibratory system will be formulated for higher degrees of freedom. And also we will look into the design of vibration absorber, for example, something which is similarly used in high risers like this Taipei 101 building, which has a pendulum absorber for absorbing the vibration. So we'll look into the design issues of these vibration absorbers. These absorbers are also used for countering large torsional vibrations in an IC engine crankshaft. So we'll look into the details of the design philosophy for these. This will be followed by a more involved modeling and analysis of a multi-degree of freedom system, when you have examples such as this gearbox, where you can see the shaft has so many inertia elements where you cannot model this as only fewer degrees of freedom. So when large degrees of freedom are involved, then how do you model that, how the governing equations are obtained, and how, more importantly, to find out computationally efficient way of getting the response of such multi-degree of freedom system. This, of course, will be followed by some of the other advanced level topics such as numerical methods involving transfer matrix or FEM, continuous systems, and maybe some introduction to the condition monitoring. Now, the examples again are like in the case of a guitar or a violin strings. These strings are constant diameter, long stretched strings, which are more aptly modeled like continuous systems rather than a fewer degree of freedom. The music box cantilever that you see here maybe can be modeled like a continuous system, but if you closely look at these cantilevers, they are actually having variable cross section, and therefore it would be more appropriate to model it as using transfer matrix method or through FEM. So these are all the topics that you have in this particular course. The USP of this course is going to be many practical problems and lab sessions, interesting discussions related to the phenomena that we learn from these topics. So who can join this course? UG or PG students. UG students of course can join, but even PG students who haven't had this vibration as a first course in during their undergraduate studies can definitely join for this interesting subject. Branch can be anything, but of course it is more suited for students from mechanical, aerospace, or civil engineering background. The basic prerequisites is just the basic understanding of engineering mechanics and engineering mathematics, that anyway every engineering graduate learns in his first year. On a lighter vein, anyone who doesn't feel nauseated at the sight of ordinary differential equations, or do not hate the Newton's second law of motion, or won't mind some of the sine and cosine terms or the complex quantities floating around in my slides, they are good to go and can register this without doubt. You will enjoy the course and we look forward to having you with us. If you have any doubts regarding the quality of teaching, these are the testimony of my past students of this particular course which I have taught here at IIT Delhi in the past. The team is, I am going to be assisted by two of my doctoral research students in the lab, vibration research lab at IIT Delhi, and their pictures are shown here just to let you know whom to blame if there is something that goes wrong in the conduction of the course apart from me. So thank you, and we look forward to having you in this course. Thank you very much.